Okay, good morning. Let's start with today's lecture. And today we start with public key or asymmetric cryptography. And the first topic that we cover today are digital signatures. Probably the most important primitive that we have. And I think it's even more important than encryption, because if you don't have public digital signatures, our complete infrastructure breaks down. There are no certificates, period. And without certificates, there's nothing that we can do. And I will talk about certificates at the end of the course. Okay, good. So digital signatures are meant to provide message authentication. You know this picture already. We have Alice and Bob that want to communicate. And in authentication, they want to make sure that they really receive the messages unmodified by the person they think that the message came from. So in this case, in our case here, Bob wants to send a message to Alice, and Alice wants to make sure that the message is really from Bob, not from Eve, and that Eve did not modify the message while it was transmitted from Bob to Alice. And we saw one way to achieve this, namely message authentication codes. But message authentication codes have their limitations and problems, in particular limitations that we would like to avoid. In particular, in message authentication codes, you need to have these shared secret keys. And what we really would like to have instead of message authentication codes is equivalence of handwritten signatures. And message authentication codes do not provide equivalence of handwritten signatures because they only guarantee authenticity between two persons. Only two persons that share the key can really use a certain message authentication code together with the shared secret key. In handwritten signatures, you can sign everything, and everybody basically can check your handwritten signature. Right? Well, usually not. That's not really true, but we pretend it's true, right? By providing your signature, you at least sort of vouch for the document that you have signed. We'll see how we can do that with digital signatures. So what we want, instead of message authentication codes, we really want to have digital signatures as equivalents of handwritten signatures. As such, they provide authenticity and integrity. And they also provide, and that is the difference to message authentication code, non-repudiation and public verifiability. And those are two things that we know from handwritten signatures. Public verifiability means that everybody can check the validity of a document. You just look at the signature, usually we just see that there is a signature, or in case that has become more common in the recent days, again, you sign a sheet of paper and then somebody compares the signature on this little sheet of paper to your signature on your credit card or EC card, right? So this is called public verifiability. And the other thing, and that's obviously not provided by message authentication codes, because in order to verify in a message authentication code, you have to have the secret key, and usually only two persons share the secret key. And the second thing that differs or that differentiates signatures from message authentication codes is non-repudiation. One cannot deny having signed a document. Okay, this is something that we usually want from signatures. I mean, if you sign a contract, the meaning of your signature is you vouch for the authenticity and integrity, and you really bind yourself to the terms of the contract. Right? You bought, I don't know, a house for a certain sum. And then you cannot deny later on, once you have moved into the house, used it for several years, well, I want my money back because I never signed a contract, right? So this is meant by non-repudiation. This is also not provided by message authentication codes because at least two persons have the shared secret key, right? And you cannot tell which of the two persons actually signed or a very computed attack. So these are two things that on top of authenticity and integrity, we will achieve using digital signatures. And as such, they really are equivalents of handwritten signatures. And although the legal requirements for digital signatures are much harder than for handwritten signatures, they provide much better security than our handwritten signatures. It's just that those are more common and we are used to them, but digital signatures usually are much, much better. Okay? Okay, so these are the two things, or the four things that we want to achieve with digital signatures. So they really become equivalents of handwritten signatures. In particular, they can then be used to sign contracts. Okay. Okay, good. So then what is a digital signature? As usual, as we are now used to in this course, I provide first the syntactic definition of a digital signature, tell you how we use them, and then we talk about security to achieve authenticity, integrity, and non-repudiation, as well as public verifiability. So a digital signature scheme is a triple of algorithms consisting of a key generation algorithm, a signature signing algorithm, and a verification algorithm. And since we are now talking about asymmetric or public key cryptography, the key generation algorithm typically is much more important, more complicated, and it's a real important ingredient of digital signatures. So the key generation algorithm on input 1 to the n, and as usual our security parameter, outputs this time a pair of keys, sk and pk, and the meaning of the security parameter is that those keys should have length at least n. In terms of bits, those are usually, we represent everything as a bit string, but they have a mathematical meaning. But as a bit string, they should have a certain length or size. That is what we mean here. And then the signing algorithm gets as input 1 to the n. It gets the secret key and a message, say from 0, 1 star, and outputs a signature, sigma, that we obtain by using the secret key sk and the message m. So this is as in message authentication codes, but here we use, in message authentication codes, we use the shared secret key k. Here we use a secret key to sign. Okay? Now the verification algorithm is a deterministic algorithm. It gets as input 1 to the n. In the future, I'll mostly ignore this 1 to the n. It gets only the public key, and it gets a message m and a signature sigma, and it outputs a bit b, denoted by verify with the public key m, sigma. Okay. This is as in message authentication codes, but in message authentication codes, we use the same key here as here, whereas here we use here the secret key, here the public key. Okay. And finally, we have our requirement. Sorry, I changed the format yesterday and it doesn't show up here anyway. We have the following requirement. For all n and all key pairs generated by the key generation algorithm, for all messages, if we first sign message m with secret key sk to obtain a sigma, and then we verify with the corresponding public key from this pair and the message m, then we should get back 1. 1 meaning we accept. Okay. So this means that if you generate a signature with a secret key and verify it with the corresponding public key, that should be accepted. Okay. Yeah. So this requirement, correctness requirement, is similar to, again, message authentication codes, but here we used here and here the same key. Here we use here the secret key, and they're the public key. And since we have these pairs, and we use different keys for signing than for verification, we call this either public key cryptography or asymmetric cryptography. The asymmetricity I'll explain in a second. Okay. Now, as usual, here I said that we can sign messages from 0, 1 star. Often in our first constructions, we cannot achieve message space 0, 1 star. Instead, we can only, given a certain public key generated with the key generation on security parameter, and we can only sign messages of a certain length. And we call those things, again, signature schemes with fixed length message length. Right? So in this case, for all n and all pairs generated by gen with input 1 to the n, the signing algorithm works only for messages of a certain length, L of n, where L of n is typically a polynomial. Okay. So here, what did I? Oh, so again, these are all polynomial time algorithms. Right? This is, and only the third one, the verification, here we will require that it's deterministic. Right? These two are really probabilistic polynomial time algorithms. So the signing can also involve randomness. The key generation algorithm should involve randomness because the key should be unpredictable at the end of the day. Okay. So how do we use these things? Let's go back to our view of the communication between Alice and Bob, where they want to make sure that Eve doesn't interfere with the communication in the sense of changing the messages. So what we do here is, so in the first place, Bob, who wants to send messages to Alice, okay? He uses the key generation algorithm, and he generates this pair, SK, PK. And he keeps this secret key to himself. That's why it's called the private or secret key. But he sort of publishes the public key under his name in, say, a key database. Okay? So that everybody can look it up. And so when Alice wants to receive an authenticated signed message from Bob, well, what she does is, well, she gets Bob's public key from the database. And then when Bob wants to send a message, he just uses his secret key, he signs the message, and instead of just sending the message, he also sends the signature with the message. And on the other side, Alice, upon receiving this pair, checks that the verification yields 1, that it accepts. This is similar to message authentication codes. Okay? Yeah. Now, the important point to notice, of course, is not only Alice can retrieve the public key from the database, but Eve, as an attacker, adversary, can do the same. It's public, right? So everybody can access and retrieve the public key. So Eve can do that as well. So if we talk about security, we always have to keep in mind that the adversaries have the public information as well. So in the private key setting, we said that they do not get the key. Here, they get this half of the key. And that has consequences for how we have to generate keys and what kind of properties key pairs should have. Also, and that explains the term that we also often use, asymmetric cryptography. In message authentication code, one key was good enough for the commutation in both directions. If you have the shared secret key K between Alice and Bob, you can use the same key to send messages, authenticated messages from Bob to Alice and from Alice to Bob. Here, if now Alice wants to send an authenticated message to Bob using the signature scheme, she has to generate her own key pair. Okay? And then if she wants to send a message to Bob, she has to use her secret key, and Bob has to retrieve Alice's public key in order to then verify the communication, the message. Okay. So here, keys are can only used in one direction, not the other direction. So it's asymmetric. Okay, keys can only provide communication, secure communication in one direction, not the other, and not in both directions, which is a symmetric case. Okay. Okay, let's go back here. If you go to this, or let's just go stick with this picture. So since Alice and also Eve can retrieve the public key, but Eve should not be able to sign messages in Bob's name, we obviously need that the public key should not allow you to compute the secret key. Right? If you can, from the public key, compute the secret key, you may as well not use the scheme at all. Because then everybody can retrieve the public key. If the end can compute the secret key from the public key, everybody can impersonate Bob. So secret keys must be hidden even if you get the public key. Okay. Also, we want that signing and verification, this correctness requirement. So public and secret keys have to fit together, so that if we sign with one half, we can verify with the other half. Yeah? Or in the secret key, often we assume that the secret key includes the public key as well. Right? Everybody has a public key, so the signer has a public key as well. Right? Okay. So we need to have, usually these things need to satisfy certain mathematical properties. They have to fit together such that the correctness requirement can hold. Okay. So it's not as in the symmetric case, message authentication codes or encryption schemes, that secret keys just are arbitrary bit strings. They need to have a mathematical structure so that they fit together. And also that from the public key you cannot recompute the secret key. Okay. So there will be much stronger requirements on the keys. Not every bit string will be, or pair of bit strings will be a legitimate key pair in a signature scheme, as we will see later. Okay, so this is what we should always keep in mind. Also notice this picture here is a simplification. In practice, it looks more complicated. In particular, this part here, sort of, how do you make sure that the public key really belongs to Bob and was not exchanged by something else? The solution is we use digital signatures. And then that leads to certificates. But I'll talk, as I said, I'll talk about this later. Okay, so this is the syntax of digital signature, and we also looked at how we used digital signatures. So now we should talk about the security of signature schemes. Okay, and what we want to provide, obviously, is unforgeability as in message authentication codes. Right? An adversary should not be able to forge on a signature on new messages. Okay? However, so that is what we want. An adversary should not be able to generate a valid signature, even though he knows the public key PK of the correct signer. Because public keys are made public, everybody knows them. So that's different from message authentication code, where the adversary does not get the secret, the key. Here he at least gets the public key. Okay? And then again, similar to what we had in message authentication code, this should be true even if the adversaries get signatures on messages of his or her choice. But obviously the adversary must then compute a new signature for a new message. Here in message authentication codes, if you remember, we had the strong unforgeability and weak unforgeability. Strong unforgeability, a new message tag or signature pair. And weak was signature on a new message. Here we only consider weak security. This is usually good enough. There are a few cases where we really need strong. You can modify the definitions, and then most of the things actually provide strong security anyway. Okay, and so then as usual, this is our general strategy. We only consider probabilistic polynomial time adversaries. We limit them in their abilities. And the adversary should only succeed with negligible probability. So these are our usual stuff. This is the stuff that we know from message authentication code. The first half of this sentence is what we know from message authentication code. The second part, that's really the difference. The difference in our setting. Okay, let me go back again here. And because we have these secret and public keys, and only one person knows the secret key, that only means non-repudiation, right? Because only one person should know the secret key. Nobody else should be able to compute the signature. So if you see a valid signature for a certain public key, there's only one person, if we have something that's secure, that should have been able to compute the signature. So it has to be you who did that. And you cannot deny that. That's a consequence of the security. The public verifiability is provided simply by this picture here, by the syntax of this scheme. Okay, how do we formalize this? Well, obviously we do that using a game and then our usual sequence of definitions and notations. Right? And the forging game is very similar to the forging game that we saw for weak security of message authentication codes, with again the difference that we provide the adversary with the public key. Okay? So let pi be a signature scheme, and then we define the signature forging game for pi between a challenger C and an adversary A as follows. The common input is 1 to the n, and then C chooses a key pair using the key generation algorithm, and C gives the public key to the adversary. Then the adversary asks the challenger for signatures on adaptively chosen messages M1 through MS and gets the corresponding the corresponding signatures. Note, we need the secret key to compute signatures, but the adversary only gets the public keys. The public key. And then we collect the messages M1 through MS in this set Q. And eventually, but after polynomial time, polynomial n, A outputs a pair M, sigma. And A succeeds, and the result of the game is 1 if there are two conditions that are satisfied. So the pair M, sigma must verify using the public key that was generated in the first step, and M must be a new message, not one that the adversary queried before. Okay? So this is the conditions that we had for weak unforgeability or weak security for message authentication codes. Okay? And if that's not true, then the result is 0. Good? The reason we model our game in this way is, as in the message authentication code, we always assume that adversaries can observe past communication, and they may even be able to induce entities to sign messages of their choice. but then they want to create signatures on a message, of a new message. Okay, and as usual, we write sign forge a pi of n for the output of the game on input 1 to the n. So for each n, the game is defined, and this is a value. Or actually, this is a random variable. Right? Over all the randomness that we use in this game here, the randomness that's used in the key generation algorithm, the randomness that A may use here, it may use here, and then that's it. Right? So there's lots of randomness involved. So it's a random variable. And we say that the signature scheme is existentially unforgeable under adaptively chosen message attacks or simply secure if for every probabilistic polynomial time algorithm there is a negligible function mu such that the probability that this random variable is 1 is this negligible function. Yeah? This is always the same. I will call this simply secure in the literature. You often see this abbreviation for this: existential, unforgeably under chosen message attack. Sometimes you see a little a in here to indicate that it's adaptive. That is in cases where people also consider other security concepts where they have an S in here. But since I only, often they just use this terminology. But I will simply call it secure. Note that this here, if a scheme is existentially unforgeable under adaptively chosen message attack, this implies that it's hard for adversaries to compute the secret key from the public key. Because if you succeed in computing the secret key from the public key, obviously you have the secret key and then you can sign any message you want. So in particular, you will be able to win the signature forging game. Okay? So this implies in particular that we cannot compute the secret key from the public key, because the public key is given to the adversary. Okay, let's look at a signature scheme, a poor one, an insecure one, but we can make it secure under certain conditions. But it shows you what kind of mathematical structures we are going to use and how we really have to have keys that key pairs that nicely fit together. And the one thing that we look at are the RSA signatures. They're often called, what I present here is often called the textbook RSA signature. Textbook, because it's the one that you find in textbooks, accidentally it's not secure. That it's in textbook doesn't imply that it's not secure, right? But it's the one that you often find in many textbooks, and some textbooks even without mentioning that it's insecure and that this is not what people use in practice. Okay, but it's good as a good example because it can be made secure and it shows you the kind of mathematical structures that we use. Okay, we need a few mathematical prerequisites. So by Zn, I denote the integers modulo n. So and let's do here an example. Yeah. So let's assume that n is 35. Let's do 55. Okay. Then Zn is simply, it consists of all residue classes mod n. So usually I would denote this the residue class, so the class that consists of all elements that modulo n modulo 55 are equal to 0. So 0, 55, 110, and so on. Although later on I'll just write 0. And then you have the residue class 1, and eventually you have the residue class for 54. 55 is the same as here. And this is a ring. We do look at it with addition and multiplication modulo n. Why it's a ring structure. If I look at this here, under the addition, that's a group. Right? If you add two elements, you get back an element in the group. You have a neutral element, which in this case is simply 0, or the 0 representative class, and there are inverses. Right? Just if the inverse of an element, C is simply 55 minus C. And then if you 55 minus C plus C is 55, 55 is in the same class as 0. Done. However, that n with multiply is closed. So if you multiply two elements, you get an element back from the group. It has neutral element. Oops, recall that then you don't look at the 0 for a ring as in a field. Note neutral element that is 0, but it does not have inverses for all elements. And also distributive law and commutativity, all these things are satisfied. But you do not have necessarily inverses. For example, the element 5 here does not have an inverse. Why is that? Because the GCD of 5 and 55 is not 1. You cannot have a GCD in that case. However, if we restrict this Zn to the set of integers that have a GCD 1 with n, and that is independent of the representative of the residue class, as one can easily see, and we denote this thing by Zn star, then in this subgroup, or in the subgroup of this thing here, then we have inverses. Those things really do have inverses. That's the extended Euclidean algorithm, as usual. Okay, and phi of n is the size of Zn star. So in our case, what is phi of 55? It's a number of elements that are GCD 1 with this thing. Turns out to be 40. Okay. Why is it 40? So which elements do not have this thing? All multiples of 5. Well, because 55 is 5 times 11. 5 and 11 are prime numbers. So if you do not have GCD 1 with 55 as an element here, you either have to be a multiple of 5 or you have to be a multiple of 11. Okay? There are 11 multiples of 5 in there. Well, 0 times 5, 1 times 5, up to 10 times 5. 11 times 5 is 55, which is the same as 0 times 5. You have 5 multiples of 11, right? 0, 11, 22, 33, 44. So these are the elements that do not have GCD1, except that I counted the 0 twice. Right? So I subtract 1 because I counted 0 twice, which gives me 15, and those are the elements in Z55 without Z55 star. And then you subtract 15 from 55, and that gives you 40. And this is the size of Z55 star. You can also check it, count simply the elements that are relatively prime. 1, 2, 3, 4, 5 not, but 6, 7, 8, 9, 10, 11 not, and so on. Okay, and as I said, A in Zn has a multiplicative inverse in Zn. That means an element A to the minus 1, so that A times A to the minus 1 is 1. 1 is a neutral element with the multiplication x if and only if the GCD of A and N is 1. And you can even compute that. You use the extended Euclidean algorithm, take care of these coefficients in there, and then you get the inverse. Okay. And also there is a nice formula for phi of n, which is basically what I did with 55 over there. It says that phi of n is simply you take the prime factorization of the thing, you subtract, these are from pj, ej, you subtract pj, ej minus 1, and multiply it. Subtract certain elements that cannot be cannot have GCD1. You can prove that, it's not too difficult. What you get is that phi of n is n times 1 minus 1 over pj. You pull out all the pj to the ej's, that gives you the n, and what's left here, if you pull out pj to the ej, here it's a 1, and here you get 1 over pj. If you really want to prove that formally, you should use the Chinese remainder theorem. But never mind. And you can check here that this is true. In the case of 55, the ej's are all 1. So I subtract from every prime 1. 5 minus 1 is 4. 11 minus 1 is 10. 4 times 10 is 40. So we get our 40 back. Okay. An important case, let me mention that, is, I squeeze this in here. If n is equal to p times q, p not equal to q, p, q prime numbers, then phi of n is simply p minus 1 times q minus 1. The ej's are all 1, so this ej minus 1 is 0, so this becomes a 1. Okay. Good. Now we are ready to talk about textbook RSA. And I will use this example, and I will erase this immediately. Can I do that already, or? Okay, good. Then let's do that. N is 55. That stays. Yeah. So, how does the key generation work in textbook RSA? So, on input 1 to the n, we choose 2 primes, pq, uniformly at random from this set here, from the interval 2 to the n minus 1 up to 2 to the n minus 1. These are exactly the numbers that can be represented with exactly n bits. Right? For this here, you need n ones, and for this here, you need n minus 1 zeros and a single one, just the other way around. For this, you need n ones, and for this, you need n minus 1 zeros and a leading one. Right? Okay, so in our case, I don't want to provide you with a little n. Say here we choose p and q to be p is 5. Q is 11. I don't want to make a big example because you won't see anything from huge examples. Okay, and then what we do next, so that these are two, then we set n to be the product of the two, which is 55, and we also compute phi of n, which is in our case 40, as we just mentioned. Then we choose an element uniformly at random from Z phi of n star. So phi of n. Not so, let's say here we have E to be 3. Okay? It's legitimate because, let's say GCD of 3 and 40 really is 1. Okay? And we compute the multiplicative inverse, which exists because it's in here, of 3 modulo 40, which in this case, d here is, d is, what is d? 3, I forgot, and I didn't write it down, I think. 3, 39, okay, good, it's easy. 3 times 13 is 39, which is minus 1 modulo 14. So we should take this to be 13 times 13 is 169. 9 times? Yeah, good, 9. D is 9. Is that right? Let's see. D is 3 times 9 is 20. No, that's wrong. Okay, let's check. So 3 times 13 is 39, right? Which is minus 1 modulo 40. So if I multiply 3 times 13 times 39, then I get 1 modulo 40. Right? So whatever, so this is minus 1, so minus, this is the same as minus 13, and minus 13 is 27 modulo 40. So 3 times, is 1 modulo 40. If you don't believe me, 3 times 27 is 81, which is 1 modulo 40. Well, anyway, good. So D is 27 in this case. Don't worry about my internal computations. It's not so important. Okay, good. So that would be, and now we set the public key to be n, e, and the secret key to be n, d. Okay. And you may wonder, well, part of the public key is also part of the secret key. Yeah, but the other part you hopefully cannot compute, so that's good enough for our purposes. Now we do a signature scheme of fixed length. So on input 1 to the n and secret key sk, which is n, d, and a message, and now I choose the message 0, 1, the message space is 0, 1, 2, n minus 2 for some reason that I'll explain, and interpret m as an element in Zn and output simply m to the d mod n. Yeah? So let's do m here. So in our case, well, I don't. So here, little n, if you want to do that, little n is 3. Is that right? No. Yeah, this already doesn't work very well. Let's say little n is 4. That doesn't really work because you can represent 5 with 3 bits, but never mind. Okay, so this is really. So assume that so what we do here is, in any case, such a bit representation we interpret as an element in M. Right? So let's do something here. Say M is equal to 7, say. Okay. Then the signature n, d of M is equal to 7 cube, right? Which is 49 times 7, which is 9 times 7, which is 23 mod, which is, sorry, this is not, so this is 9 times 7, this is 12 mod 55, right? 7 to the 7, this is all wrong, sorry. This is complete garbage. So 7 times 7 times 7, modulo 55 is something. So this is 49, right? 49 is minus 6 modulo 55. Now I'm working modulo n. Here, with these d's and e's, I work modulo phi of n, but here I work now modulo n. Right? Easy to remember, if you do something in the exponent, it's modulo phi of n. If you look at the base, it's modulo n. So this is 7 times 7 is minus 6 times 7, which is minus 42, which is equal to 13 modulo 55. Right? If I did it correctly. Looks good, I think. Yeah. Yep. Okay. Okay. The verification now is on input 1 to the n, public key, n, e. What we do is we simply compute sigma to the e and output 1 if that gives us back m. Okay. I don't want to do this here, but you can hopefully check that this works out. What I want to mention here, it's y 0, 1 to the 2n to the minus 1, because I can interpret these things as uniquely with elements in Zn, even if I look at leading zeros. So these bit strings you can have to just look at the size of these things here, and then you can check that these are unique. If they were not unique, you would immediately get into trouble with the security. Also, there are many other ways of generating RSA keys. So this is really the key generation algorithms. There are more clever ones. And I didn't even specify the details so far, right? How do you do these things? But before I do that, so before I provide some of the details here, let's see that this really is correct. Okay? Correctness requires that if we first sign with the secret key and then verify with the public key, we get a 1. What does that mean in this case? In this case, we look at sigma to the e, which must be 1, which must be m, right? But sigma is m to the d. So m to the d times e for correctness, we must have that m to the d times e is equal to m mod n, right? For all m. Okay, this is what we need to prove, that this is correct. Yeah? And how do we do that? I only want to go into one particular case. Namely, we look at the case where m comes from Zn star. So m is relatively prime, has GCD1 with n. In that case, there is this famous lemma by Euler, or Gauss, Lagrange in generalizations, which says that for n in n and m in Zn star, we have that m to the phi of n is 1 mod n. So here's phi of n, here's n. Here we have Zn star. For these things outside of this set, this cannot be true because they have a common divisor with n, and then you cannot get 1. So why does that help us to prove this statement here? Well, if we have that m is in Zn star, we can divide by m. There is a multiplicative inverse, right? So I can, this here is equivalent in that case, so m in Zn star. This is equivalent to saying m to the e d minus 1 is equal to 1 mod n, right? I have a multiplicative inverse. I can on both sides multiply with the multiplicative inverse. Okay. What does that mean? I'll just erase this part here. But now we see why we choose the keys the way we did, because remember, E times D is equal to 1 mod phi of n, right? Go back. D is the multiplicative inverse of E modulo phi of n. So we must have this relation here. This is equivalent to saying that there exists a number in Z such that E times D minus 1 is equal to K times phi of n. Right? Ed minus 1, this is Ed is equal to 1, which means that the difference of the two things is a multiple of phi of n. Let's say this is even an element in n. Yeah? Now, if you go back here, then EdM to the Ed minus 1 is the same as m to the, well, k times phi of n, right? But this is the same as m to the phi of n to the k. Now we can use our lemma. This here is 1, so this is 1 to the k, which is 1 mod n. And we are done. Okay. Yep. The general case, you use Chinese remainder and this here. I don't want to go too much into the details. Okay? Obviously, this here leaves out many things, right? How do we choose a random prime, and how do we verify that things are primes, that the number is a prime number? How do we pick? Well, this here you should know, right? This is Chinese remainder, extended Euclidean algorithm. But in any case, the prime generation, we choose, how do we do that? We choose a random number in this interval, that's easy. Choose a random bit string starting with a 1. And then test whether p is prime. If so, output p. If not, go back and choose another p. And that works. The efficiency is how often do we have to repeat? Right? How often do we have an expectation go back to this first step because we did not pick a prime? Well, there exist many primes in this interval. This is the so-called prime number theorem. It's a consequence of the prime number theorem, which states that roughly the fraction of elements in this interval that are primes is roughly 1 over n, little n. So you go back n times roughly, and then you have a prime. There are better ways to do this, but that's okay. And then we have to check whether a number is prime, and that we can do using the so-called Miller-Rabin test, which is the one that people use in practice. There's also a different one called the AKS test, slightly different. AKS is deterministic, Miller-Rabin is probabilistic, but never mind. Right? So we can do that, because there are many primes, and we can check whether a number is prime. This part here, the exponent generation, you choose E to be z from z phi of n uniformly at random, and you check whether its GCD is 1. If so, you compute D with E times D is 1, and output E and D. Otherwise, you go back to step 1. And again, the same thing happens here. The number of, or the fraction of elements that are relatively prime to a number is large. It's even better than in the prime case. And we can test efficiently whether whether two numbers have GCD1, that's Euclidean algorithm, and then extended Euclidean algorithm to get this thing back. Okay. In practice, you do something different. You pick E to be 3. So you probably, if you do online banking, you do have an RSA secret key and public key with a bank. And in roughly 95% of the cases, E is 3. The primes are usually picked in such a way that phi of n is really not divisible by 3. So here it's D then differs because you have all of us have different n's with our banks, hopefully, and hence we have different D's, which are hard to compute from these things. So and then so we can easily we can generate keys efficiently. Signing and verification, well, we need to do these exponentiations, right? Well, you know how to do efficiently exponentiation. You do not do m times m times m times m times n. Instead, you look at the binary representation of E and do square and multiply. Right? In our cases, these things in RSA, the numbers P and Q are huge. Little n in practice here, this little n, the size of the primes, little n tends to be today 1024. So you use primes with 1024 binary digits, which roughly means something around 350 decimal digits. Okay? So these are huge numbers, and you don't want to m times m times m times n, this huge number. That would be for D. So you really need to use square and multiply. But you can do that. And then everything is nice and easy. As I said, for the key generation, there are more efficient methods. I just wanted to convince you that you can do it. But there are other methods where you generate numbers in such a way that they are already guaranteed to be primes. So you don't need to do this repetition all the time. Okay, good. This, if you ever wondered why you learned about square and multiply in data structures and algorithms, this is the reason. In cryptography, it's you need that. You can't get away without it. Okay, good. So, questions about this? If not, then, well, the disappointing part is, so it's syntactically, it's a digital signature. Unfortunately, it's totally insecure. I can easily forge, even without chosen message attacks, because the signature under 0 is 0. 0 to anything is 0. The signature under 1 is 1. 1 to anything is 1. Never mind. The signature of -1 is -1. Well, unless you have n as a multiple of 2, which you don't do. You use always 2 large primes. And large primes is not 2, right? So then these things are -1 gets mapped to -1. And usually the exponent that you use, d, is odd. It has to be odd. You can do even things better. If you want to forge a signature under message M, now you really want to forge a specific M, the signature. Now you use your adaptively chosen message attack. You cannot ask for the signature of M, because then the signature would not be a legitimate forgery. You ask for the signature of 2 to the e times M, which you can compute. Right? What is the signature of 2 to the e times M? The signature under 2 to the e times M is 2 to the e times m to the d, right? This is 2 to the e times d times m to the d. This here is 2, right? And this is a signature under m. So this is 2 times the signature under the secret key of m. Right? Now, if I multiply that thing with 2 to the -1, with the inverse of 2, I get the signature under m. Bad. So you can even forge signatures under messages of your choice using this adaptively chosen message attack. But these things already are sufficient to show that RSA is insecure. Why is it so insecure? The exponentiation and the exponentiation is multiplicative, right? The exponentiation of the product of 2 messages is the product of the 2 exponentiations. The function is homomorphic. The encryption and also decryption function is homomorphic. That's way too much mathematical structure to be secure. And the way to make RSA secure is provide methods to destroy this homomorphic property, as we will see in a later lecture. So textbook RSA is insecure. That doesn't mean that RSA is completely useless, but we have to combine it with different techniques to get something that's secure. Let me briefly also cover the observation that we already made. For a signature scheme to be secure, secret keys must be efficiently computable, must not be efficiently computable from public keys. Right? Otherwise, it's dead. Right? What does that mean here? Given n comma e, the element d with e times d must not be efficiently computable. The secret key consists of n and d. N, yeah, it's part of the public key, forget it. But d should not be efficiently computable given n comma e. That in particular means that if you're also given n. If you can compute, given n, the primes p and q, you can compute d efficiently from n comma e. Because if you have the primes, you have phi of n, which is p minus 1 times q minus 1, as I said before. And if you have phi of n and you have e, it's easy to compute the multiplicative inverse of e mod phi of n. Use the extended Euclidean algorithm. So this is necessary, but maybe not sufficient to prove that in RSA, at least we have that secret keys cannot be computed efficiently from public keys. Well, in fact, there is a converse to this, which says that if you can compute from n comma e, you can compute this d, then you can also compute the primes. Okay. So that this is the content of this theorem. That's harder to prove, much harder to prove. So if you can compute p comma q, then you can compute d. But if you can compute d, you can also compute p and q. So these are really equivalent of each other, but there may be other ways of breaking RSA, which we'll come to later. So it all comes down to the question then, given computing d from n comma e, comes down to the question, how difficult is it to compute p and q, given n? Right? And the answer is, we don't know, but we do have certain algorithms that factor. What we really want to do is factor, right? Given n, we want to factor it into its prime components. Don't worry too much about this thing here. There are rather really clever algorithms to factor. And the running time of this best known algorithm, which is called the number field sieve, is e to the c times log n to the third root times log n to the 2 divided by 3. It takes some time to digest this. This is super polynomial. It's much larger than any polynomial, but it's better than something like n itself, capital N, or root n. Root n is easy to achieve. You just test all primes up to a certain bound. Right? This is much better. It's the fastest known factoring algorithm that we have around these days. There is another algorithm. This is the elliptic curve method that achieves a running time similar to this, except that you replace 1/3 and 2/3 by 1/2. These exponents typically add up to 1. But it only depends on the size of the smallest prime factor. Okay? So if you have an n with unbalanced prime factors, one is much larger than the other, that degrades your security. Okay, that's why in RSA, and as we did it in our key generation here, let's go back even further. Here, we wanted the two primes to be roughly of the same size. And the reason we do that is because of this elliptic curve method, because that says if you choose them of very different size, you lose security. In any case, I don't want to talk too much about this, although this is a very interesting topic. These algorithms explain why we choose the primes so large as we do today with 1024 bits, and why we choose them of the same size. With this algorithm in practice, you can factor today numbers that have around 150 to 170 decimal digits. Okay? Cryptographers are always paranoid, so they say, look, you can factor bits, it's numbers with 170 bits. Let's make our numbers much, much larger. We pick our 2 primes of size 350 decimal digits, and n has 700 decimal digits, so much larger. But computers also tend to get faster, and so these things in practice increase. So for high security applications, the recommendation today is already use primes with 2048 bits. So roughly 700 decimal digits. But yeah. Good. So this was our little detour in one specific signature scheme, but you saw that we really need this fitting together of secret and public keys. And we cannot just choose arbitrary bit strings. So the next topic that we'll tackle after the break is how can we construct digital signature schemes from general assumptions. And that will take a few steps. And the first step will be in constructing so-called one-time signatures, which we'll do in the second half of today's lecture. Now let's make a 15-minute break. We meet again at, say, 9:45. And then I'll talk about this. Okay, good. See you then. Okay, so let's continue. So now that we have seen what digital signatures are, and we saw an insecure example of it, we want to construct secure digital signatures from general assumptions. And the assumption that we need for digital signatures is one-way functions must exist, if and only. If digital signatures exist, one-way functions exist, and if one-way functions exist, we can show that also digital signatures exist. So digital signatures exist under the same assumptions that CCA secure symmetric encryption schemes exist. So in this lecture, I will only show that secure digital signatures exist if one-way functions and collision-resistant hash functions exist, but collision-resistant hash functions imply existence of one-way functions, so collision resistance is enough. Later on, in a subsequent course, I will replace or indicate how we can replace collision-resistant hash functions by so-called universal one-way hash functions. And those can be constructed from one-way functions. So really, and the techniques are basically the same. So to get these secure signatures from with these universal one-way hash functions, then collision resistance is almost the same. And the steps, so we cannot do that directly. We also did not construct CCA secure symmetric encryption schemes directly. Instead, we had intermediate steps where we try to achieve weaker security notions. And here we do the same. In fact, what we will do is we will look at so-called one-time signatures first. And we will show that we can construct those one-time signatures from collision-resistant hash functions and from one-way functions. Again, we have to take a detour here, fixed length messages, arbitrary length messages, and the step from fixed length to arbitrary, that's done by these hash functions. So first we will start with one-time signatures and start with one-time signatures with fixed length message from one-way functions. Then we replace the fixed length thing, and then we'll replace the one-time by arbitrary. It turns out that we really need to have one-time signatures with arbitrary message length to go to fully secure signature schemes. Okay, so let's first define what one-time signatures are. It's syntactically, it's the same as signatures. It's a security notion that's different. And to define this, we define a so-called one-message signature forging game for a signature scheme between a challenger and adversary. It's all the same as in our forgery game, except that A is only allowed to ask for the signature under a single message. So that's all. The rest then is the same. He outputs a pair, and he succeeds if the result of game, if he outputs a successful signature, and it's a new one, which in this case we can simply write down by saying it's not the same as the query message. Right? That's all. So he's only allowed, so if you, that means, and then we can do our usual stuff, right? You know what's coming here, it's a one-time secure, blah, 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 right? What does that mean? If you go back to the game, such a signature is secure as long as you use a secret key just to sign a single message. If you just use every secret key just once for a single message, then it's okay. Right? Because given a signature under a single message, this says you cannot compute a second signature for a second message. So that's one time. You can use it once, okay, but not twice. Okay. So then when we have to go from one-time signatures to arbitrary signatures, we somehow have to modify our signature scheme so that we guarantee that we use all secret keys only once, that we have to. And there are various techniques that we look at. Okay? So If you one-time secure one-time signature, you use it once and you are secure. No adversary can forge a second signature unless with negligible probability. Yeah? And we can obviously say, again, we have a signature scheme for fixed length messages, also one-time signatures for fixed length messages. It's not really anything surprising here. Okay, do you remember one-way functions? One-way functions means easy to compute in this direction, hard to invert. Compute in the other direction. Okay. And so now we want to, given a one-way function, we want to construct a one-time signature. And this construction is known as Lemtort's one-time signature. And the construction doesn't use the construction can be done obviously with any function, only the security follows them from one-wayness. So assume that we have an arbitrary function f from 0, 1 star to 0, 1 star that's polynomial time computable. So you can efficiently evaluate it. In the terminology of the Monday's lecture, there's this machine MF that can evaluates the function. Then the signature scheme pi f is defined as follows. The key generation is this here, the rest is very simple. So the key generation is a little bit complicated. So the key generation on input 1 to the n, it chooses 2n values from 0, 1 to the n. So for I from 1 to n is an index between 1 and n, and b is a bit. And for each index bit combination, and there are 2n of those, I have a bit string of length n. And I said, so this is called xib. And I say yib is the function value of xib under function f. And I organize these things in a 2 by n matrix. So for each index, first index, there are 2 second indices, 0 or 1. The 0 indices, the one with the 1 I, 0, I put into a first row, and with the 1 index as a second component, I put in the second row. Yeah? And correspondingly, I can organize the YIBs. This is the secret key, this is the public key. And my message space is also 0, 1 to the n. So it's a fixed length signature scheme. Okay? So, and to sign a message M0, 1 to the n, I output, let me write this down here, then I can visualize this better. So I have here my x1, 0, x2, 0, and so on, xn, 0, and I have x1, 1, x2, 1, up to xn, 1. So my message corresponds to m bits. So the mi's in 0, 1. And then I pick out elements from this matrix depending on the bits of m. And for each column, I pick one bit, one element. And the bit in m determines whether I pick in that column from the first row or the second row. Okay? So assume that my m is, say, 1, 0, 1. In between is something I don't worry about. Okay? Then my signature in the first column, I pick the thing according to M1. which is a bit, so that makes sense, right? It's 0 or 1. And 1 here is 1, so I pick this element. In the second element of my thing is then determined by the second bit of my message. So I go to the second column, because it's second, but then I pick here 0, this guy here. And so on until the last bit. This n here, the length corresponds to the number of columns I have in here. So now I can here, this is a 1, so I pick this here. Right? So sigma here is x1, 1, x1, 0, and x2, 0, xn, 1. So I just pick according to, from each column I pick one. Which one I pick is determined by the bit at the corresponding position in M. Right? To verify a signature, we compute the corresponding Y's. Or we check that for each position, F sigma I is corresponding at YIMI. So if I picked it here, I check that this element here, F, is really this guy here. In my example, the second was 0, so I checked that here, this guy is really F of the second bit or the second component of my signature that I got. Yeah? Okay. So what's the idea? The idea is, if you know the secret key, you should, signing always means, I provide you information that I can only provide to you if I know the secret key. Or I gave you something, depending on the message, that I can only give you if I know the secret key for the signature. And here, well, I give you the pre-images of selected elements. And now you can imagine that if f is a one-way function, that should be a good idea, right? If f is a one-way function, then you should not be able to cheat. Right? Or it would be hard to forge, because if you forge and you don't know the secret key, but this is a public key, you have to provide a pre-image. You have to invert. Right? So that's the basic idea. And that's actually true. We will prove that this is this following theorem that says that this is a secure fixed length one-time signature with message length n if f is a one-way function. And it's a good idea to convince yourself that it's not stronger. That we can only prove one-time security is inherent to the scheme, not inherent in our stupidity. Right? And that's probably something you do in the exercises or tutorials. Okay. Yeah. You can actually make this here n, this that I picked here n is just because I wanted the notation to be easy. You could do this with any length, but it's fixed. You could also do it here with not 0, 1 to the n. You could do something 0, 1, 2 to the n as well. Maybe that's a nice exercise as well. But that all this doesn't help in what comes next, or in what we with the subsequent steps in our construction of secure signature schemes. Okay, so this is what we want to prove. Right? Scheme clear? So here now, then the verification would just check that. So this is sigma 1, this is sigma 2, this is sigma n. And then we would just check y1, oops, f of sigma 1 is equal to y comma 1, f of sigma 2 is equal to y 2 comma 0, and so on until f of sigma n is y n comma 1. Okay. Okay, so we need to prove this. And the way we prove this, you can imagine what we do. Let A be an arbitrary adversary against the one-time forgery game against the scheme. From this, we construct an adversary A prime that attacks the one-wayness of F. And here is our step from forgers to inverters. So let A prime be the forger, and then we construct an inverter A. Yeah? So I'll write this down so that the notation is clear. So proof that A prime be an arbitrary but fixed adversary in one SIG-forge. Let me check that I do the right notation here and not one sign forge A pi. And let epsilon n be denote this advantage of this guy here. Oops, where is it? Oops. This one sign advantage of A. Sorry, this is A prime, A prime pi f of n. Need to show that epsilon n is negligible. So from A prime construct adversary A against F in this inverting game. In invert. Okay. And okay, so how do we do that? And the technique that we use here is similar to is a variant of the index guessing game. So we need to guess an index. So in this inverting game, right, recall that A gets a y that is f of x for an x chosen uniformly at random from 0, 1 to the n. And it has to find an x prime such that f of x prime is equal to y. Yeah? Do we have to go back to that, or do you remember? So that is what we have to do. So it gets, on input, it gets such a y as f of x for an x in 0, 1 star, where x was picked uniformly at random. So now we sneak this element y into our public key for the signature scheme. We sneak that into one of the positions of the public key. And we guess the position, or we pick a random position. So we choose I star from 1 to n, uniformly at random, and we pick a uniform bit. And then for all i's, ib that are not this particular index pair, we pick an xib uniformly at random from this here, and set yib to be xib. And we set y star, b star to be y. So in the position that we guessed here, or that we picked here, we sneak in our y. Okay? So somewhere in here is our y. Now our hope is that if A prime forges a signature, that it uses this position. That it picks a message that it forces it to reveal a pre-image for this y. And once if we succeed with that, we have our x. That is a pre-image. Right? So more concretely, we now simulate A prime with this public key. Okay? And when A prime, it can only ask for a single signature, right? When A prime requests a signature on message m hat, we do the following. If m hat at index I prime has the value b prime, yeah? This really means it has hit this guy here. Yeah? At this position here, here it is. So m, say I star. We have here m hat I star 0, and we have here m hat I star 1. One of them is this y. It must pick either this or this, right? Because at position I star in its message, there is a bit. If we are unlucky and it picks the one where we have put in our y, we abort. Why do we abort? We don't know the pre-image, right? Because that is exactly the thing that we try to find. But if that is not the case, so if at the column I star it picks the other bit, then we know all the pre-images. Because all the other pre-images we have picked ourselves. There's only one position where we did not pick it, in which case we have to abort. Okay? Otherwise, we return the correct signature, and we are able to do that. Yeah? Now, when A outputs a message signature pair, where sigma is x1 through xn, we do the following. If mi star is not equal to b star, unfortunately, again, it picks the wrong position. Right? Now we want to hit it this position. right? Because if it provides a forgery there and it has hit our Y position, this guy here, it has to provide us for a correct signature, it has to provide us this X, which f of x prime is equal to Y. If it did not do that, we abort. We get things that we know anyway, because we all generated them ourselves. But it does, if it has this property, then we output xi star. Yeah? So in this phase, we want that this m hat is not this b star, not the row corresponding to b star. In the forgery, we want it to hit there. Okay? Okay. And we hope to be lucky with this choice. Yeah? Now, if it's a valid forgery, we have found a pre-image. Right? That's clear. Valid forgery means fxi star evaluates to y. And we are done. We have what we want. Okay? And also clear is that if A prime is PPT, then A is PPT. Why is that? We have to pick this here, the indices, easy. For all things, we have to pick these things and then we have to evaluate f, but f is polynomial time computable. So this can be done in polynomial time. We have only 2n many applications. 2n is in polynomial, polynomial times polynomial is polynomial. We simulate A prime. It's good. Polynomial time. Check. Equality, easy. Return, easy. And here also, all this is easy. To check whether it's a valid forgery, we just have to apply f once to see whether it really gives us our value that we need. Yeah? So A PPT, A prime PPT, then A is PPT. So that's easy. But now we need to analyze this inverting success probability for A. So need to analyze probability let's call this delta n. Okay? Yeah? So let's do that. So delta n, what is it? It's a probability that the simulated A, the simulation of A that I do here, right? Of A prime that I do here, outputs a forgery. And here we do not abort. Yeah? In for A, we have 2 aborts, and I mean that abort. And M I star is equal to B star. Huh? We do not, we output a valid forgery, so f of xi star is this y. We hit the right position here at the position where we sneaked in our value y, and we did not abort here. Okay? Okay. Now we condition, but we condition on something that sounds a little bit strange, but anyway, we condition this way. So this is the probability that mi star is equal to b star conditioned on simulated A outputs forgery and not abort times the probability of these two things here, right? Definition of conditional probabilities. Yeah. Now this part here, or this probability, I can again use conditional probabilities. Okay. So, and I do this condition on the non-abort. So this is this probability times the probability of simulated A prime outputs forgery condition on non-abort times the probability for non-abort. Again, just using the definition of conditional probability, because there we have this part here, right? It's an end, and I condition on this part here and multiply with the condition, with the probability for the condition. Yeah? Well, nothing really interesting happened. So let's analyze these three probabilities. So we need to analyze this, we need to analyze this, and we need to analyze this here. So let's do the easy case. Probability of non-abort. Well, oops. Uh-oh. Naja, gut. Jetzt hat er gesagt 10%. Oh. Okay, good. Non-abort, mi star hat b star. Well, at this position, there are two possibilities, right? We are in column I star. We pick this uniformly at random. And this is all done independently from everything that A star does. So that happens with probably 1/2, 1 out of 2 choices. This guy here, if we do not abort, and the conditions in, this guy here, what if non-abort, what's the simulated A prime outputs a forgery? Well, that is exactly epsilon n. If we do not abort, then we answer the query correctly. All things are generated as in the real forging game, because we pick these things here uniformly at random. This here was picked in the inverting game uniformly at random. Everything looks exactly as in the real game. So this guy here is epsilon n. Okay? So it remains to analyze this guy here. Yeah? And I claim that this guy here is at least 1/n. Okay. I will prove that in a second, but when I've done that, we conclude then if we have all these things, this and this and this leads to delta n is at least epsilon n divided by 2n. Or equivalently, epsilon n is less than 2n times delta n. But we know that delta n is negligible because we have a one-way function. Negligible times polynomial is still negligible. Epsilon n is negligible. We are done. Yep. So this guy here remains. Okay. I erased this already. I'll keep the last few lines in there. I should also keep this. So we need to analyze this probability here, right? And what we can say that is conditioned on non-abort. Is equivalent to I star is in the set of all i's where mi hat is not equal to mi. Where m hat is the query message and m is the forgery message. Okay. Under non-abort means we do not have that this here is the same. Right? So then the fact that mi star is the same as b star can only be the case if and only if I is one of the indices where they differ. Otherwise, it doesn't work. Okay? But then the probability, and we also know that this set here has size at least 1, since m hat is not equal to m, using the fact that we also condition on we output a valid forgery. Yeah? But we pick this index uniformly at random. So we must pick over all elements from 1 to n, one that sits in this set, but there is at least one element in there. Hence, the probability of picking one from that set is at least size of this set divided by size of all indices, which is n. So size of this set divided by n. The set has size at least 1, larger than 1 over n. And we are done. Ja. Ich hoffe, dass da noch 5%. Okay. Okay, good. So that's how we. Ich bringe den sonst mal mit und lade den in der Pause auf. Deshalb funktioniert das. Okay, so this is how we do this. This 1 over 2 to the n intuitively hit the right index. There are 2n indices, hit the right one. Right, sort of. This is like how I always remember it. The proof is a little bit subtler than what we did. Okay, questions about this proof? So it's our standard proof, reduction proof, plus index guessing, where we guessed where he will provide sort of the index where he really provides a new thing. and that's and he must provide a message that differs from the one that he queried, and we sort of guess the position where he provides the new thing. Good, as usual, it's one-time signature. We want it really secure, and it's fixed length. And what's even worse, if you look at what we constructed, the keys are much longer than the messages that we can sign, right? Keys consist of a 2 by n matrix, each entry of length n. So 2n squared is the key length, whereas the message length is n. That's not what we usually want. We want to be able to sign arbitrarily long messages with short keys. So what we need to do is we need to be able to, in our signature scheme, to decouple the key length from the message length. Keep the key length, but then be able to choose an arbitrary message length. And we use this and achieve this with either collision-resistant hash functions or universal one-way hash functions. And you probably have heard about this paradigm hash then sign. So what we do is we pick a so-called hash function. Hash functions consist of a pair of key generation algorithm and an algorithm H. The key generation algorithm outputs a key, which is a bit string. And the H is deterministic. It takes that input 1 to the n, a message, and it outputs a bit string, HS of x. And it did not, here should be, it's in 0, 1 to the L of n. Okay. This should be in 0, 1 to the L of n. And that L of n is called the hash length. And we can also do it for fixed length messages, not for all 0, 1 star, but blah, blah, blah. You know what the story is. The important thing here is the collision finding game, the security notion we use for it. And the collision finding game is that the challenger chooses the key and gives S to the adversary, and then the adversary has to output two x's, x and x prime, that map to the same function value, to the same hash under H of S with the key S. That's a collision. Okay? And these are really now keyed hash functions. Sometimes you see them without keys, but here it's keyed hash functions. Quite simple. Security notion clear. We do the usual thing. And the construction that I'll analyze next time is hash then sign. We take a signature scheme. We can take a hash function. The key generation generates a key for the signature scheme. It generates a key for the hash function. The signing now consists, first of all, by hashing the message and then signing the hashed message. That's it. That's here. But for that to be useful, we need that the hash values are part of the message space for the signature scheme. Right? These things must be end up in the message space for the signature scheme. Right? And that's why I said the signature scheme is with message length L of n, and the hash function has hashes of length L of n. Then this is guaranteed. So you first hash, then sign. And to verify, well, you simply get the message M, you hash it, and then you check whether the verification is true on the verification of the signature scheme is valid on the hash value. And I will repeat this next time, and I'll also prove this is actually secure if the signature scheme is secure and the hash function is collision resistant. And it's easy to see that we need the collision resistance to some extent. We can slightly weaken it, because if you can find collisions, right, you can simply ask for the signature under our old scheme for this value for which you have found a collision, and then output one of the two messages. You did not ask for that message, so that's a valid forgery. So collisions, not being able to find collisions is necessary to some extent. As I can say, we can weaken it a little bit in the case of one-time signatures. But if you have collision, ask for the signature on one of the messages. That's also a valid signature for the other message that leads to the collision. You're done. We'll analyze that next Thursday in more detail. This is a construction that is used by almost any signature scheme in practice. Combination with SHA-2, SHA-3, some secure, practically secure hash function. So this is one of the most important constructions, also in practice. Okay, so I think my laptop is running out of energy, so I'll guess we stop here for today and continue with the proof next time. Okay, good. Thank you.